Okay, good morning, afternoon, or evening, everybody. Welcome to Session 1 for the NASA Aquarius Data Training Webinar Series. This is your host, Jennifer Brennan. I've got 2 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started here. Thanks to everybody who entered early and has been so patient. I would like to begin by going over just a few logistics related to this webinar. First, to ensure best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you'll find that located on the lower right-hand side of your screen. This works like a chat. This webinar is being recorded and will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a few days of completion. And what I plan to do is email participants with these links when Session 1 has been posted. All presentation and video files will also be available for download at the end of the webinar. Today's session will be 1 hour and 30 minutes long. 1 hour is allocated to the presentations, with the final 30 minutes being dedicated to an optional question and answer period. After our speakers have finished their presentations today, what we'll do is I will provide some closing information regarding the wiki, and from there we will move to the question and answer period. As a reminder, you will have an opportunity to ask your questions throughout by using the Q&A pod. Questions will not be answered using the raising hand function. It has been disabled. All right, so today's speakers are Annette Descharon, who is the NASA Aquarius Science Communications Lead located at the University of Maine, Dr. Tony Lee, who is the NASA Aquarius Project Scientist at the Jet Propulsion Laboratory, and Dr. Vardas Santos, the lead data engineer at NASA's Physical Oceanography Distributed Active Archive Center, and we refer to this DAAC, excuse me, I'm getting tongue-tied here, as the PO.DAAC. With that, it is my pleasure to turn it over to today's first speaker, Annette Descharon. Annette?
Jennifer, and welcome everybody. I'd like to thank everybody so much for coming on behalf of the advice team. And here we are. This is Tony, Vardas, Leslie, myself, Carla, and Jorge. The first 4 people you see pictured there will be presenting during this webinar series, and Carla and Jorge will be helping with Q&A sessions and with the wiki. And all together, we've been really having fun designing this webinar series for you. We're offering a new type of training experience to help you prepare data for your research, master skills guided by the Salinity Science and data experts on our team, and also craft an effective take-home message, something that we want to help you with for the poster session, which is going to be session 4 of the series. So over the next 3 weeks, you'll learn about the NASA Aquarius mission, methods for finding and visualizing salinity data, and communicating effectively with the public. You know, we're going to do everything from soup to nuts, as they say in English parlance. We're going to get you familiar with how the data are acquired, where the data are stored, how to access it, how to visualize it, and also how to present any results that you come up with in your data, working with the data, and share it with your peers. We have homework assignments, as you noticed from the invites, and they're designed to be informative and fun. We know that a lot of us go to meetings and you hear people talking about methods, but there's really not a chance to try them. So these webinars themselves are designed to give you the background and show you how to do things, and then the homework assignments on the wiki are made for you to try it out. It's a friendly atmosphere. We've already got a bunch of people who signed on to the wiki, and we hope if you haven't done it, you will do it, and there will be a place for you to share what you've done and get some feedback from others. And if you do all this, by week 4, you'll be ready for the culminating poster session. We'll share details for the poster session in session 3. You can post on the wiki and not present at the poster session. That's not a requirement. It's just something to help you get toward doing the poster session if you want to take advantage of that opportunity. Likewise, you can attend the poster session and not present. So, you know, this is pretty free form. We just want you to learn about the data and have fun and, you know, basically learn how to work it up and talk about it, and that's our goal. Here is a quick overview of what we're doing each week. Right now we're in session 1 and we're welcoming you. Next we're going to have the Aquarius SAC-D basics. then data resources, and then sessions 2 and 3, as you see in the table there, are outlined. And for the first 3 sessions, there'll be an optional question and answer period after the fact. And session 4, if you choose to take this opportunity, will feature you and what you've done. So with that, I'd like to turn this over to my colleague, Tony Lee at JPL, who's the Aquarius project scientist. Tony?
Thank you, Jennifer and Annette, and welcome everyone. My name is Tony Lee from the NASA Jet Propulsion Laboratory, and I'm the project scientist for the Aquarius satellite mission. And today I'm going to go over some basics for Salinity Science from space and the mission design for Aquarius to measure salinity of the global ocean with a target accuracy. What is salinity? Salinity is a measure of the dissolved salts in seawater, and the average salinity of the open ocean is about 35 grams of salt per 1,000 grams of seawater. So very often you hear about 35 parts per thousand or 35 ppt. So it's a ratio of the weight of the salt and the weight of the seawater. And very often salinity is expressed as a unit called practical salinity unit, or PSU, which is a dimensionless unit. Now in the lower graph, it shows the composition of salts in seawater, and most of the salts in seawater is sodium chloride. And the composition of the salts in the seawater is more important for chemical oceanography, but not so much for physical oceanography. So I will not go into the detail of that. Now, where do salts come from? Salts in the ocean are mostly coming from land and volcanic sources, and they are washed down into the ocean or got dumped into the ocean and stay there for a long time, typically thousands of years. Now, what changed the salinity pattern in the ocean? Well, first of all, the motion of the oceans, or ocean currents, they move the salinity of fresh water in the ocean around and change the salinity pattern in the ocean. And salinity are also influenced by the different elements of the water cycle, such as evaporation that increase the salinity, precipitation that dilute the seawater and reduce the salinity, and sea ice formation. It rejects the brine or the salt into the seawater and increase the salinity nearby, and when the sea ice melt, it dilutes the seawater and cause lower salinity. River runoff from continents will dilute the seawater and cause a lower salinity as well. So all these elements of the water cycle work together to change the salinity pattern as well. And ocean salinity integrate all these effects of the different elements of the water cycle, and therefore it provides a good indicator of the changes on the water cycle on a certain space and time scale. For example, on basin to global scale, and on decades and longer time scale, is a good indicator of the changing water cycle. So now, how is salinity measured? Now, traditionally, salinity is measured by ships. And so in the picture in the lower left, it shows the HMS Challenger, which undertook the so-called Challenger expedition back in the late 1870s. It took near global measurements across the Pacific Ocean, Southern Ocean, and the Atlantic Oceans. And it's sparse, basically limited to a few tracks, but it does traverse these different oceans, and it's the first global scale ship-based measurement of the salinity. And it took 1,000 days and encompass about 68,000 nautical miles. And later, there have been various merchant ships and research vessels that took salinity measurements over more regions of the global ocean, including the Indian Ocean that the Challenger expedition did not get into. The picture on the lower right shows the pattern of the salinity based on the past 100 years of ship-based measurement, and this is before the era of the Argo array, and the Argo array has about 3,900 autonomous profiling flow in the oceans, and that is a major advancement in situ salinity measurements. So, but this picture here shows the historical ship-based salinity measurements before the Argo era. And you see some major patterns of the salinity, such as in the subtropical ocean. For example, the subtropical Atlantic, which is dominated by high evaporation, and the salinity is generally very high. And in high latitude oceans, where you have river input and sea ice melt, it generally has lower salinity. And the same thing is true in the tropics, in the tropical rain band and near river outflow area, and you will see generally lower salinity than in the subtropical area. But the in situ database are really too sparse to characterize the global salinity pattern, as you see that there are many gaps in the salinity pattern as shown by the in situ historical in situ data. So the Aquarius mission has pioneered NASA's satellite missions to measure global salinity measurements. And here the animation will show the dynamic salinity evolution in space and time that is captured by the Aquarius sensors. Aquarius was launched in June of 2011, and the data begin in August of 2011. And by June of 2015, the mission ended due to a power failure. And this animation shows the salinity pattern captured by Aquarius from August of 2011 to June of 2015. Now, just to point out some features of salinity as seen from the Aquarius measurements. Well, first of all, you see that the Atlantic Ocean is a lot saltier than the Pacific Ocean, and that is because of the high evaporation and the moisture transport from the Atlantic Ocean into the Pacific Ocean, and the fresh water got dumped into the Pacific Ocean, and some of the moisture transport from the Atlantic will also carry out into the Southern Ocean. So the Atlantic Ocean has a net loss of water compared to the Pacific Ocean. Now, if you look at the contrast of the subtropics versus the tropics, you see that the tropics under the rain band here in the Atlantic, as well as here in the Pacific, that's called the Intertropical Convergence Zone, or ITCZ. And in the Pacific, there's also a rain band called South Pacific Convergence Zone, or SPCZ. These are large tropical rain bands that are associated with heavy precipitation. So in this area, you see low salinity compared to the subtropics in all oceans that have higher salinity than the tropics. Now, Aquarius also vividly described the evolution of the river plumes. For example, the Amazon outflow in the Northeast Atlantic, that in one season, the outflow goes to the northeast and in another season, it retroflects into this current called North Equatorial Countercurrent, and those fresh water traverse across the Atlantic and influence both by the river plume of the Amazon flow and the intertropical the precipitation of the Intertropical Convergence Zone, or ITCZ. Now, in the Indian Ocean, you see very dynamic salinity variability with high salinity in the Arabian Sea and the low salinity in the Bay of Bengal. And that is because the Arabian Sea has warmer temperature and has higher evaporations, and whereas the Bay of Bengal has a large amount of river discharge from the Ganges River system. And also during the summer monsoon, the wind that goes this way, it carries the moistures from the west into the east, and some of those rains are dumped into the Bay of Bengal, so it makes the Bay of Bengal even lower in salinity. So if you look at the contrast of the Arabian Sea and the Bay of Bengal, it's like a small microcosm of the contrast between the Atlantic and the Pacific Oceans.
Okay, wonderful.
Thank you. So now I'm going to go over some basic principles of how salinity is measured from space. Now, the salinity instruments from NASA basically measure the microwave emission from the ocean surface in terms of a variable or parameter called brightness temperature. And it measures the brightness temperature in the top 1 centimeter or so of the ocean. Now, the brightness temperature is related to the sea surface temperature through a coefficient, and that coefficient depends on the incidence angle and a constant called a dielectric constant of the seawater, and the dielectric constant depends on the surface temperature, salinity, and roughness, and the radio frequency. So there have been various theoretical models that describe how the brightness temperature relate to the surface temperature and salinity and radio frequencies. So a commonly used model is one by Klein and Swift, developed in the late 1970s. And here the graph on the right-hand side illustrates the dependence of the brightness temperature on the y-axis on the sea surface temperature in the horizontal axis, and on the salinity as illustrated by the different curves in the graph, and that is at L-band frequency of 1.4 gigahertz at zero incident angle. Now, if you look at for a certain temperature in the warmer water, for example, 20 to 30 degrees or so, and that's tropical waters, when you change salinity for the same amount, let's say from 37 to 32 PSU, you will see a larger change of brightness temperature, that's in the vertical, than what you have seen in cooler water, right? So the change of brightness temperature here in warm water is significantly larger than the change of brightness temperature in cold water for the same change of salinity. And therefore, this L-band sensor, L-band radiometer, has better sensitivity in the tropics and subtropics than at higher latitude oceans. So the first proof of concept of the L-band radiometer for measuring ocean salinity is from this Skylab, which is the first space station of the United States in the 70s. Now the graph here shows the measurements measured by Skylab's L-band radiometer expressed through antenna temperature, and I will explain in a minute how antenna temperature is related to brightness temperature. It shows the dependence of the antenna temperature on salinity. So even without all these corrections of the surface roughness and surface temperature and other factors, you already see a relation between the antenna temperature and the salinity. Now, antenna temperature is basically a measure of the brightness temperature, but it's affected by the incidence angle and atmospheric absorption. So after correcting for the incident angle and atmospheric absorption effect, one could derive the estimates of the measured brightness temperature from this antenna temperature. And after Skylab, various prototype instruments have been developed to attempt to measure salinity from space. And out of those, the PO.DAAC sensor, which stands for passive active L-band and S-band sensors, that was developed at JPL, is the basis for NASA's Aquarius, and as well as the soil moisture active passive or SMAP mission. Now the PO.DAAC sensors, it has 1.4 gigahertz L-band radiometer integrated with a 1.26 gigahertz L-band radar. Now, the purpose of the radar is to correct for the surface roughness effect on the radiometer measurements, which is the most important correction needed in retrieving salinity from the L-band radiometer measurements. So there are two major factors that affect the radiometer measurements in addition to salinity, and those two factors are surface temperature effect and surface roughness effect. So the radar measures the surface roughness and allow for the correction of the surface roughness effect, and the Aquarius use surface temperature measurements from other satellites to correct for the sea surface temperature effect on the radiometer measurements. And so what's left from the measurement is then reflecting sea surface salinity variation. And so that's basically the major principle of retrieving salinity from this kind of sensors. So the picture on the left is showing a control experiment that is testing and calibrating the PO.DAAC sensor. The right-hand side shows a picture of the PO.DAAC sensor being loaded onto a C-130 plane for a field campaign in the Monterey Bay, California for CalWell, calibration validation of the PO.DAAC sensors. So how did it go? That field campaign in the Monterey Bay, and here is the graph shows the measurements, the retrieved salinity from that field campaign, shown on the y-axis as a function of the longitude along the flight path of that field campaign. Now the yellow dotted curve here shows the retrieved salinity before one correct for the surface roughness using the radar measurements. But after the surface roughness correction was applied, what you have is the magenta curve, which is now much closer to the blue curve, which is the ground truth based on ship observations. So this illustrates the importance of having a radar measurement for the surface roughness to correct for the effect on the ocean salinity. So now some more information on the mission design of the Aquarius. So the Aquarius sensor was flown on board of the SAC-D spacecraft provided by Argentina. The mission is a joint collaboration between NASA and Argentina's Space Activity Commission acronym, CONEA, C-O-N-E-A. So CONEA provided the space craft called SAC-D, which is a Spanish acronym that stands for scientific applications. And D is just the series of the SAC-D platform that CONEA provided. So it was launched in June of 2011, as I mentioned, and scientific data begin to be delivered in August of 2011. The target accuracy of Aquarius is 0.2 PSU on the scale of 150 kilometers, which is the nominal footprint of the Aquarius radiometer. And it's also that target accuracy also apply for the monthly averages. So now here the animations shows the kind of the sampling characteristics of the Aquarius satellite. Give me 1 second. And the color, so after 2 months, it begins to deliver data as shown by the color. And so the color there basically shows the measurements along the swath of the Aquarius, which I will describe a little bit later. And then, so now it's gonna, you see the sensor come up again. The satellite comes up again. And so Aquarius has this sun-synchronous orbit that will provide measurements, and with its swath width on 7 days, it pretty much covers the entire global oceans, as you see in the animation here. Okay, next. Yep, okay. Now a bit more about the instrument design. One of the major factors that make it possible for Aquarius measurement to achieve the target accuracy of 0.2 PSU for salinity is because of the very precise radiometer. And in fact, Aquarius radiometer has a precision of 0.1 Kelvin, which is the most precise L-band radiometer ever built. And a rule of thumb of the translation of the precision of brightness temperature accuracy into salinity accuracy, it's roughly a factor of 2. So 0.1 Kelvin roughly translates to about 0.2 PSU of accuracy in salinity measurements. And another major factor that allowed the 0.2 PSU to be accomplished is the onboard scatterometer that measures the surface roughness. Because, as I mentioned, the correction for surface roughness effect is the most important factor in salinity retrieval. And of course, there are other designs of the Aquarius orbits and sensors that allow it to achieve that accuracy as well. So a bit more about the mission designs. The Aquarius has 3 radiometers that measure brightness temperature at L-band. Each of those have 2 polarizations, so they provide the sensitivity, different sensitivity for the measurements. And the picture here in the lower right, it shows these 3 beams or horns of the radiometers with different incidence angle and different footprints that measure the brightness temperature. And together they form a swath width of about 390 kilometers, which is the width of that color swath that you saw in the earlier animations. Now, the Aquarius is on a sun-synchronous orbit with a 6 p.m. Local equatorial crossing time for the ascending node and 6 a.m. for the ascending node. and the solar panel points to the sun to get the power, whereas the radiometer point away from the sun to avoid the sun glare. Otherwise, the measurements would have been contaminated. And so the animations here will show that the animations here again is just show the sampling characteristics of the Aquarius missions that help achieve its swath and the sampling over 10 days that cover the entire globe. So that's so much about the orbit and sensor design. Now Aquarius, even though the mission has ended in June of the operation, even though the operation has ended in June, the Aquarius project is still improving the data and providing the last version of the Aquarius data, which will be version 5, sometime later this year or next year. Now, even though the mission is going to end after June of next year, the legacy of Aquarius hasn't. And in fact, NASA has launched the SMAP satellite in January 2015, and even though the SMAP mission was designed for land applications, the Aquarius team has used its experience to retrieve salinity from the SMAP satellite with a very encouraging qualities. So if you are interested in the specific quality of the Aquarius data, especially to describe temporal changes on different spatial and temporal scales, and how it compares to the capability of the SMAP data in terms of quality, I'll be glad to discuss with you offline or later in the Q&A session. But before I end, I just want to point out that the SMAP satellite has about 40 kilometer spatial resolutions compared to the 150 kilometer resolution of the Aquarius satellite. And that presents a major advantage in studying coastal and marginal sea salinities, because it not only has better resolution, it also comes closer to the coast. So with that in mind, I'll stop here and I will transfer to Dr. Walter Santo from PO.DAAC to describe the resources for Aquarius data in terms of distribution, user support, and documentations. Walter?
Hello, hello everyone. This is Vardis Santos. I'm the data engineer at the PO.DAAC, supporting the Aquarius mission and salinity in general. In this session, I'm going to give you a little overview of Aquarius data resources that are available at the PO.DAAC. So, before we begin, first of all, how does the data actually get from the satellite all the way ultimately to the end user, you out there? So there's a variety of data transfer and processing steps involved, and I'm going to briefly describe that through the schematic diagram. I just want to point out that, as Tony mentioned, the satellite is no longer in transmitting data, so we're no longer in science operations mode. And the part that is not grayed out reflects the part of the data transfer and processing system for Aquarius that is still in effect now, today, and will be operational until the mission concludes roughly next year this time. Okay, so basically, during science operations, the satellite, as Tony illustrated with those nice animations, was orbiting the Earth continuously and transmitting data to a series of strategically placed ground receiving stations. Data from these receiving stations were then transferred routinely and automatically to CONAI, the Argentinian space agency partners in Cordoba, where they were aggregated, archived, and repackaged, and then transmitted again in an automated fashion routinely to the Aquarius Data Processing System at NASA's Goddard Space Flight Center. This is where the processing of the Aquarius data occurred and still occurs. And processing involves basically execution of a series of algorithms that have been developed by the science team, as Tony described, combined with a range of ancillary data sources, including things like SST, which is an input to the salinity retrieval calculation. And then the processing system basically implements these algorithms in software that then creates a series of data products of various level 0 through level 3, that were then transmitted again routinely and in automated fashion to the PO.DAAC. PO.DAAC serves essentially as the data archive for NASA, and through the PO.DAAC, users like yourselves could come to our web portal, access the data and related information. I just wanted to point out that that in the current phase, even though there is no data transmissions from the satellite occurring, this part of the workflow here, the improvement of the algorithm in an iterative fashion, is still ongoing. So as Tony mentioned, we are currently at version 4.0 of the data set, but the science team is working on improving the algorithms even further to produce ultimately by this year next time, the version 5 end of mission Aquarius dataset, which will be the legacy dataset from the Aquarius mission. I just wanted to point out as well, this component here, AVDS, which is the Aquarius validation data system, which is integral to the ground truthing of the Aquarius science data. And that ground truth data comes from in situ observations from the Argo global buoy float network that's continuously making observations of salinity, temperature, and other parameters throughout the world's oceans. So those in situ measurements are being assimilated into the system and compared with the retrieval, the salinity retrievals from the Aquarius satellite to compute error statistics, biases, and ultimately to further improve the algorithm that will come in the next release of the version 5.0 dataset. Okay, so a little bit about PO.DAAC. PO.DAAC is one of 12 NASA Earth Science DAACs responsible for archival and distribution of Earth science data. Each one has a specific thematic focus, and PO.DAAC, the PO stands for Physical Oceanography, is responsible for archival of NASA's physical oceanographic satellite data. We are located in California, in Pasadena, close to Los Angeles, at NASA's Jet Propulsion Laboratory. So PO.DAAC's role in this project has been throughout the mission operations has been to serve as the archival and the designated archival and distribution node for all of the mission Aquarius mission science data. PO.DAAC is more than just a data center. There is a lot of expertise in the actual data themselves, in the salinity observations themselves. And in addition to archiving the data and providing stewardship of the data, we provide a range of tools and services for accessing the data, and we provide also support services for user if they have questions about the data and how to access it. Okay, so as mentioned, PO.DAAC has supported the archival and distribution of Aquarius, but we also, related to salinity, also have archiving and distributing the SPURS, the NASA SPURS Salinity Field Campaign data. That is available via the PO.DAAC. And of course, we archive physical oceanographic satellite data for a range of NASA missions and projects that are listed here. Okay, the gateway to all PO.DAAC data resources, okay, and information on data is via the PO.DAAC portal. To get to the portal, You simply go to Google and type in PO.DAAC, PO.DAAC, and that will take you directly to the PO.DAAC web portal page. To find out more about the Aquarius mission, in the main menu, there's an item that you can select called Missions, and you can see amongst the various missions, NASA missions listed, is Aquarius. Click on that, and what will come up is the Aquarius mission page that is illustrated in this slide. Let me orientate you a little bit about this, about the layout of this mission page, because this is really a one-stop shop for all resources and information on the Aquarius mission and data at the PO.DAAC. So in the main portion of the screen is essentially a little description of the Aquarius mission itself. Further below, there are current announcements that may apply. What we see here is actually the announcement of the version 4.0 data set that was released last July on the 17th. Perhaps most importantly, though, is the panel to the right here, where you see links to a variety of resources that are grouped by category. So we're going to look at these in more detail now, but at the top we have data links, access to the Aquarius data via a range of tools and services that are listed, and then a comprehensive listing of technical documentation related to the Aquarius mission that users should be aware of. And there are three items in particular that users, we strongly recommend users take a look at. First and foremost amongst these is the Aquarius version 4.0 Users Guide. Now, every time a new version of the data is released, this user guide is updated, as is a lot of the other documentation that's available under these technical documentation links on the mission page. But the user's guide is really a key document, especially for users who are unfamiliar with the Aquarius dataset, because it describes the specification of the data products, what data products there are, the metadata that's contained, how to access the data, all manner of very, very useful information that especially a novice user of the Aquarius data will want to read about before actually trying to work with the data themselves. The second sort of key document that most users need to pay attention to is this Aquarius Salinity Validation Analysis document. As I said, an important part of the Aquarius data system is this data validation component and the comparison against ground truth, and in particular the Argo buoy data. So this document, with every new public release, in this case version 4.0 of the data set, a thorough analysis and comparison of the Aquarius retrievals against ground truth is undertaken, and any errors, biases, regional discrepancies in the data are documented in this documentation here. And so it's very important when using the data to understand the potential limitations and possible areas where errors can creep in, some of which are very regionally dependent. So this is an important document as well to be aware of. A final document that kind of relates to this whole issue of errors is something that was produced as part of the version 4.0 of the data set, and this is the uncertainty assessment algorithm document. And it essentially just documents the method of computing uncertainty and errors in the Aquarius data. Okay, another group within this page is the group of links is the data links at the top. And when you can click on Browse Datasets, essentially to get a listing of all the current version 4.0 Aquarius that are cataloged at the PO.DAAC. We'll be going more into aspects of discovering Aquarius data sets and looking at these data set catalog descriptions next week. But this is something that you can already investigate as part of your assignments. The other thing underneath is links to all PO.DAAC tools and services that apply to the Aquarius data. So the Aquarius data are accessible via a range of means, including FTP, OpenDAAP, which is a web service, the Threads web service, PO.DAAC web service tools, and some visualization and analysis software that's web-based and available through the PO.DAAC. So in follow-up sessions, we're going to be describing some of those in more detail as well. Something that users should also be aware of is the PO.DAAC forum, which we're in the process of building up and getting more inputs about. There's a whole range of useful information about PO.DAAC datasets in general, but also there is a section specifically related to salinity. So if you have questions about the data or want to look for answers to questions that you may have, some of that may already have been addressed in the PO.DAAC forum. And you can also field your questions to PO.DAAC through that forum. Finally, if you prefer to send us an email, we also have a help desk that's very responsive. Typically, our response times to inquiries within under 2 days. So any questions on the PO.DAAC data, usage of the data, how to access the data, how to work with the data within specific tools like MATLAB or some of the web-based tools that we support like LAS, then just drop us a line or try the forum once again. And that's essentially it for my presentation. Next week, we're going to be covering aspects of data discovery through the PO.DAAC portal and some of these interesting tools and services that we have online. And with that, I'm going to pass you back to Annette, who will wrap up.
Well, thanks, Tony and Vardis. That was really great, and I hope everybody enjoyed learning about the mission itself and getting a little brief introduction to the data. So I'm here to talk to you about this week's homework. I'm going to give you a little preview of that. And so you might be asking yourself, well, why homework? Well, as I said earlier, a lot of us attend webinars where people talk and sort of you theoretically understand what's going on, but the only way I find to learn, and I know that works for a lot of people, is to do something with what you've learned. And so these homework assignments are designed to reinforce content that has been presented during the webinars. We'll give you practice using various types of tools. We found the best tools out there that are free, cost-free, that will really get you really into understanding what salinity data are, and so and how to use them. Again, we're going to give and receive feedback in a friendly atmosphere. Through the use of the wiki, you can post your thoughts, post some of the little products you come up with, and we'll respond to them. We'll give you feedback on it, and ask you to give feedback to each other. And also, again, to prepare you for the virtual poster session should you decide to participate in that. You might be wondering what the level of commitment is. Each week's assignment will take less than an hour to complete, and some of them are much less than an hour, depending on just how much you get into doing it. The assignments are all due before the following webinar, so 2 o'clock Eastern the following Thursday. A quick, in case you haven't looked at the wiki yet, here is an example of the Session 1 assignment. The top of the page has background documents, the three documents that Vardis just referred to. There'll be links to those, some videos that are related to the session that aren't from the session, but other background videos that we've put together for you are there as well. There'll be the instructions. We've laid them out, tried to be very systematic in laying these out to make them easy for you. We've had other people test drive them, so we think they work. And so here's just an example of what this week's assignment is going to be looking like and how it's set up, and we hope it's clear. And if it's not, we also have this at the top here, we have your Carla, who works with me here at the University of Maine, can help to answer any questions that you might have. So just send her an email if you have something specific you want to share with her. So session 1 homework, 1 is to introduce yourself. Some of you have already done that, and so if you want to upload a picture and tell a little bit about why you've chosen to participate, that would be great. And then the other thing is the homework itself this week is to get to know sea surface salinity patterns. You've seen Tony talked a lot about what you see in sea surface salinity patterns, but what we're going to do is have you use a very simple tool to generate plots of salinity data averaged over your birthday month for 3 consecutive years. You're going to be using a tool called Live Access Server, LAS, and there's a version from My NASA Data. It doesn't have all the Aquarius data, it only has monthly averaged Aquarius. And so that will be pretty simple for you just to find your birthday month, average the data, look at 3 consecutive years, and then post those on on the wiki, on the forum, and then talk about them. What we're asking you to look for are areas of stability and areas of change. And when Tony was showing you the Aquarius movie, you probably noticed there are some areas where salinity is very stable and other places where it changes. Later, on session 3, Vardis is going to do a demo of the PO.DAAC version of this tool, which is much more complicated in terms of, but it has a lot more data types that you can work with. You can do Hofmahler diagrams. There's all sorts of things you can do with that. And so, but for this week, we're just hoping for you to take the tool, look at it, get to know salinity patterns, and share with your colleagues on what you see. So, good luck and have fun. Feel free to ask questions during the upcoming Q&A session. And there are also, as I said, email links on each of the assignment pages if you get stuck or just want to, find out something. We also have an FAQ on the wiki as well. So hopefully you will participate. We're really looking forward to it. We hope that you have fun. And now I'm going to turn it back to Jennifer. Thank you.
Okay, thank you, Annette. Thanks, everybody. What I'd like to do next is go over just a little bit of closing information before we transition to the question and answer period. And this has to do with the wiki. So when the slide pulls up here, if you have not set up your URS account, and not to worry, all of the slides from today's session, including this slide and the videos, have been posted in the file sharing pod. And I will leave the virtual meeting space open when we're finished so that, for 10 minutes or so, for those of you who are interested in downloading those files, you may feel free to do so. So if you haven't set up your URS account, getting back to that, you need to follow these steps, okay? If you do not have an existing profile or URS account, which you would have if you had ordered data before from the PO.DAAC, for example, you would go to the URL I've provided there. You will set up your profile with a username and password. You'll then need to have an initial login to the wiki. The URL is posted here, at which point, after you set up your, after you set all this up, you're going to need to send an email to support@earthdata.nasa.gov with a subject similar to, access to advice wiki, at which point one of the support team staff members will be able to provide you access and the proper permissions to view the training wiki space. Certainly if you have any questions, you can email me, or if you're having difficulty obtaining access, I will be able to get into contact with the support team members even after hours. I do work with them on a daily basis, so hopefully you don't have issues, but here's some information to hopefully help you through that process. And I know that many of you have already set up your account, so that's wonderful. And with that, what I'd like to do is actually transition to the question and answer period. And so let's go ahead and do that. And here you'll see in the lower left and right-hand side of the screen, you've got all the PowerPoints for today, including the homework assignment in a PDF format, and then also as a slide. If you left-click on any of those files, you should be prompted with an option to download the files. And on the right-hand side, you will find today's videos that were shown as well. So what we'll do now is I'm going to scroll down to see if I have any questions so far. And again, this question and answer period is optional. Some of you may opt to stay on the line. Some of you, if you've got a hard deadline, please feel free to leave. But of course, there's some benefit to having your questions answered while we have all of our presenters for the entire training series on the line. All right, does anybody have any questions? So far, I haven't noticed any. I've been trying to keep track of that as we go along. Primarily logistics oriented. And thanks for being patient, by the way, as we worked through a couple of glitches a bit earlier on. Do any of you have any questions for us? All right, great. Let's see. Hold on just a second. Okay, the first question is, I would like to know what tool Tony used to generate the videos. Tony?
Okay, thank you. Thanks for the question. And that nice video is actually made by NASA's visualization lab at Goddard. So I don't know exactly what tool they use, and they're very skillful in making animation like that. There's a large suite of those animations that very often they show it in the NASA Hyperwall in the AGU or Ocean Science meeting. Yeah, sorry, I did not make those videos.
So, Angel, I actually I'll email you with a link to the Scientific Visualization Studio site. I'll type it in here for everybody now. I believe this is going to be correct with some additional information. But the tools are generally pretty specialized, like Lightwave. We've worked with them, our team in the past, on some much longer animations, but I'll send you some information about that so you can check it out for yourself within the site, okay? And then the next question is, Laura, I would like to ask about correction. Okay, let's see, Laura. Are there any improvements to try to get close to the coast?
Yes, this is Tony. Can you hear me?
Yes, we can hear you, Tony. Thank you.
Right. So for Aquarius, how close one can get to the coast is limited by its footprint. So the footprint of Aquarius is about 150 kilometers. So if the footprint partially covered the land, and then the land signal is going to get into the antenna, and the land signal typically fluctuates a lot more than the ocean salinity signal, so that will contaminate the partially ocean footprint. Therefore, we typically mask out the data within 150 kilometers of the coast for Aquarius. So for SMAP, this will be better. One only have to mask out about 40 kilometers of the data from the coast. So it is getting closer. And another factors that could help improve the data near the coast, and by that I mean away from 150 kilometers of the coast, let's say between 150 and 300 kilometers. The data in the area can be improved by better land correction tables, essentially by knowing how much fluctuations the lands are having, so that we could remove that from the ocean signal.
Okay, thank you, Tony. The next question is, what is the name of the satellite measuring salinity? And the second part to that question is the data available at PO.DAAC? So the first part of the question, what is the name of the satellite measuring salinity, and is the data available at PO.DAAC?
Right. So the whole name of the satellite is called Aquarius SAC-D. That's the entire satellite, but the satellite sensor itself is Aquarius. And the SAC-D is the name of the spacecraft. So typically we just call it Aquarius satellite. And so I also mentioned later that NASA has recently launched another satellite that we can also get ocean salinity. That's called SMAP, S-M-A-P, and it stands for Soil Moisture Active Passive, SMAP. And yes, the data for Aquarius are being distributed in PO.DAAC, as my colleague Waters has discussed. And the SMAP data, SMAP salinity data, that hopefully will be released to the public in the next month or so, will be distributed in PO.DAAC as well.
Thank you, Tony. I just want to remind presenters, please don't, some questions just got removed, so my apologies, participants. If you click on the questions, that small X will actually delete the question. And so I did notice a couple have been removed accidentally, so we don't want that. And let's move on to the next question. I've got two here. So certainly if you don't hear your question, if you could humor us and type it back into the Q&A pod, that would be fantastic. So thank you so much. The next question is the data available regarding SMAP data? So yes, I can actually answer this. The SMAP data is available through the SAC-D, and there will also be some additional data products at the Alaska Satellite Facility DAC. I can put out, Dr. Susanto, I believe you're at University of Maryland College Park. I can actually email you with some links with information about the data products, those that are available, and you can check that out. They've got separate portions within each of their DAC websites dedicated, specifically to SMAP data products. So hopefully that's helpful.
Jennifer, this is Vardis from the PO.DAAC. Just to clarify, those are from NSIDC, those are for the soil moisture data. The SMAP salinity data should be available sometime in summer, okay, and they will be available via the PO.DAAC, not via NSIDC.
Okay, thank you, Vardis. All right, the next question is the salinity of the ocean increasing? If not, why?
Okay, that's a very good question. And actually, there are not quite sufficient data to tell whether the average salinity is increasing or not with good uncertainty. But the historical data in the past several decades has shown that the salinity in the salty area, for example, in the subtropical gyre where evaporation is high, they have been getting saltier. Whereas the salinity in the rain bands, such as in the tropics, they have been getting fresher. So the salinity contrast between the low salinity and high salinity zone has been getting larger in the past several decades. And that was in fact one possible evidence for the acceleration of the water cycle, where the rainy region has gotten rainier and the dry region has gotten drier.
Okay, thank you, Tony. The next question is, can you explain a little bit more about version 5 for the data? Or of the data?
Sorry, could you repeat the question?
Can you explain, can you tell us a little bit more about the version 5 data products?
Okay. So far, the version 4 of the data, it has already had very encouraging quality. And in particular, if you are focusing on temporal variability, right, as opposed to the time mean, which still has some issues at higher latitude, and the accuracy of the temporal change or temporal variations of the Aquarius salinity is actually less than 0.2 PSU. In the tropics, it's more like 0.1 PSU, and when you go to the high latitude, it's larger. It's larger than 0.2, but the tropical ocean, subtropical ocean have larger area in general, except for the Southern Ocean. So the overall quality is still better than 0.2 PSU. But in version 4, there's still significant seasonal bias at high latitude ocean, Southern Ocean, and North Atlantic with respect to the Argo data, which is the ground truth. And in version 5, we will be making an effort to reduce or remove this seasonal bias at high latitude with respect to the Argo data. That will further improve the quality of the Aquarius data. So that's one major improvement that we're looking forward to in version 5. And also another effort that is being made for version 5 is that we will probably use instrument-only calibration of the sensors without using any target of data assimilation product or in situ data for the global average. So the calibration does not use any ground truth or assimilation product on a regional basis, but currently it does use the global average from a global ocean data assimilation product called HICOM, which is the Navy's operational data assimilation product. It used the global average to constrain this global calibration constant of the radiometers, because the signal from the radiometer has some fluctuations over the entire global oceans. So that global reference is HICOM currently, but in the future, version 5, we will not be using that. We will use instrument-only calibration by looking at some stable target on the Earth, for example, Antarctica, in order to constrain the global average salinity without using any other data sets or assimilation product. Yeah, that's it.
Okay, thank you, Tony. The next question is referencing your slides, and it says, in Dr. Lee's slide regarding PSU, there is a 35. I don't know what that means.
Okay, so 35 refer to the ratio of the weight of the salt to the weight of the seawater. So it's 35 grams of salt per 1,000 grams of seawater. So it's a ratio, really, or sometimes people call it parts per thousand. Did I answer the question correctly? If not, I will try to clarify it again.
So for that participant, if the answer has not provided enough clarity, just if you don't mind typing into the Q&A pod, that would be fantastic. In the meantime, our next question is the SMAP ocean salinity technology and precision similar to those of Aquarius?
Right, that's a wonderful question. SMAP was designed for land applications such as moisture. So the precision of the radiometer is no match to the precision of Aquarius radiometer, which, as I mentioned, was 0.1 Kelvin. It's the most precise L-band radiometer ever built. So, but SMAP has better spatial resolutions. So the spatial average could help knock down some of the random noise in the data and improve the accuracy. And so the experimental product or beta version of the SMAP salinity product that we've been looking at have a overall global accuracy of about 0.26 PSU, and that compared to 0.2 PSU or less for the Aquarius salinity data. So you see that the accuracy of the SMAP salinity product is still not as good as the Aquarius data, and it may remain so in the future just because of the limitation of the precision of the radiometer. However, it does produce better resolution. And so if you're looking for application in coastal area where the signals are big, you know, near River Plume, for example, and SMAP data does present a significant advantage.
Okay, thank you. The next question is, what is the relationship between salinity and soil moisture?
Okay, so as far as technology is concerned, radiometer, the L-band radiometer have sensitivity to both soil moisture and ocean salinity, and that's why one could use the same L-band radiometer to measure soil moisture on land and salinity over the ocean. Now, in terms of the physical relation and how the changes in one are related to another, So that's a question of how the water cycles are connected from the ocean to land. So one example that I could give is, for example, in the subtropical area where you see very high salinity, right? That's the area that you have a lot of evaporation, and the evaporation greatly exceeded the precipitation, and those evaporated water provide the major source of moisture, which will be carried by the atmospheric circulation to land and precipitation. So those precipitation got carried from the evaporated area of the ocean and dumped on land and affect the soil moisture. So in fact, if you the SMAP satellite mission provides soil moisture and ocean salinity together. Same thing is true for Aquarius, even though I did not mention it. The two together is a really powerful tool to study the linkage of the terrestrial elements of the water cycle with the oceanic element of the water cycle.
Okay, thank you, Tony. The next question is, will NASA plan to launch Aquarius 2 as an Aquarius follow-on mission?
Yeah, I would love for that to happen. But the way NASA works is that currently several agencies, including NASA, are commissioning the National Academy of Science and the National Research Council to perform a study called Decadal Survey of Earth Science and Application from Space 2017 to 2027. So the community will provide input for the science priority and what mission should go forward and what not in the context of Earth system science priority consideration. And once they provide that recommendation to NASA, and NASA will make the decision and a priority of what missions to go forward. And yes, we are working actively with the community to prepare some white papers and proposals to have a follow-on mission that is not just focusing on ocean salinity, but in the context of water cycle study, something that can do ocean salinity, sea ice thickness, and soil moisture, and all of those together.
Okay, thank you. The next question is it possible to get the salinity data of the inland water bodies such as salty lakes using Aquarius?
So Aquarius footprint is about 150 kilometers, and even for SMAP, it's 40 kilometers. So I don't see that in the next decade or so, a spaceborne satellite will be able to get salinity in inland body water or lake. Well, if talking about a Great Lake, yes, there's hope, but smaller body of inland water and estuaries, it's not likely to happen very soon. So we are actively working with coastal oceanographers and technologists to find out how we can use different technology to get salinity for near the coast, like estuarine, delta, and inland water bodies.
Okay, great. Thank you so much. And the next question is, how is the 0.2K precision defined? Is it the standard difference with in situ measurements?
Oh, that's a wonderful question. In fact, that question is not very well defined. It can be well defined only if there are ground truth for the same definition of spatial scale, which is 150 kilometers, and time scale, which is monthly time scale. But unfortunately, there are no direct ground truth on the scale of 150 kilometers and monthly time scale, because in situ data are point-wide measurements, such as those from Argo floats and ships. So therefore, when we do collocation of the satellite measurements, average over some space, say 150 kilometers, and over a month, with collocated Argo flow measurements within that regions and time, we need to account for the uncertainty of the in situ data in representing the average salinity within that spatial average and time window. So that it's important issues, and I'd love to go into more detail about that, and just submitted a paper on that to look at the consistency of Aquarius data with the Argo data on different scales, 3 by 3 degree, 10 by 10 degree, and for different time scale as well, seasonal time scale, interannual time scale. And so if you contact me offline, I could provide more information to you. But I just want to make the point that accounting for the representation uncertainty of the ground truth data on the footprint of the satellite is very important, because there are already high resolution ship track data showing that there are very large spatial changes of salinity within the footprint. And so point-wise measurement like Argo does not completely capture or average those variability, especially in regions where you have mesoscale eddies, such as near the western boundary current, or regions with transient rain effects, such as the intertropical convergence zone.
Okay, thank you, Tony. I am looking to see whether or not there are any further questions. We've still got about 12 minutes left to our question and answer period. And I did indicate, Tony, that for the user who asked the question, I will provide you with his or her contact information so the two of you can follow up offline.
Sure, certainly.
Are there any further questions? We'll give it a minute or two. And what will happen next is, if there are not any further questions, what we typically will do is, again, I will leave the meeting room open. Given that we would be finishing a little bit early, I'll leave it open for 15 minutes or so. So for those of you who are interested in downloading today's presentations, again, on the left-hand side, you'll find all of the PowerPoint charts that were presented today. If you left-click on any of them, you should be prompted with an option to download the file. Excuse me. Again, just a reminder that within a couple of days, possibly tomorrow, I will have a link to the recording, so that if you would like to download the presentation files at a later date, you can do so by visiting our online Adobe Connect webinar catalog. We've got well over 50 webinars for the last few years, different topics, of course, or you can check it out on our NASA Earth Data YouTube channel. So just a couple of reminders there. And again, we will leave the meeting room open. However, we will be logging off from the telecon portion of the webinar. But I don't see any questions right now. Again, I'll give it a little bit more time. I would like to thank everybody for joining us today, and I don't know whether or not Carla or Annette or Tony or Vardis, if you had anything to add.
Not for me, and thank you very much for the participation, and thank you very much for organizing and hosting the webinar.
Well, it's my pleasure. Annette or Carla, did you have any closing remarks?
I just wanted to thank folks for joining us. We hope that you learned a lot. I even learned some things today, which I think is great. Also, again, we would strongly encourage you to try the homework assignments and get active on the wiki. I think you will find some like-minded people out there and get to share your thoughts and your results, and get some feedback, which is always nice doing it online. So thanks again for joining us.
Okay, and then one other reminder for those of you who may have joined today as a guest. Let's see, I'm trying to think where we still have this advertised. If you go to, it would be a good thing to register, or at least shoot me an email so that I know that you'll be participating as a guest for either session 2, 3, or 4. If you go to earthdata.nasa.gov, there should still be a link. If you scroll about a third down the page, there are a number of articles, but also an announcement for this particular training series. So registering will be a little bit easier in that you just go to the login and enter your email, and then we can keep track of who's attending each session. All right, or send me an email letting me know that you'll be participating. Well, thank you so much, everybody.
Jennifer, actually, I have one more thing to say. I'm sorry to interrupt. I just wanted to let people know that, we've talked about the coverage of Aquarius near coasts and how SMAP data are going to be better in that regard, and that SMAP data are coming. I just want to let folks know that a lot of the things they're going to learn, almost everything they learned doing the homework and through this webinar series, they're going to be able to apply to SMAP data. So just because you're learning it using Aquarius doesn't mean that you can't apply it to SMAP. So don't feel like you need to wait for the SMAP series, because it's the same sort of skill set that you'll need later. So just let folks know that.
Well, that's a very good point. Thank you, Annette. All right, well, thanks so much, everybody. What we'll do now is we will log off from the telecon, and at this point, again, I'll leave the meeting room open for another 15 minutes or so. Certainly, if you have any questions, you could feel free to either email Carla. I think that's included in one of the slides, or you can email me, and I will put you in contact with any of our presenters or co-organizers. And I hope to see all of you online next week. And fantastic. Thanks so much. All right. Bye-bye, everybody.
Thank you. Bye-bye.
You're welcome. Thank you, Tony. Bye-bye.
Thank you. Bye.
Bye-bye.
Bye. Thank you, Annette. Bye.
Goodbye. Bye. Bye-bye.